Hello everyone. So in the previous video we have discussed about a test in the field for determining permeability. That means we have discussed about a field test, okay, for determining permeability. Now in the field test diagram, uh, what we took was, if I show you the image, like this was the main diagram of the test that we had discussed. Now you see, this hole is a soil mass. Okay, it is a soil mass, and this was the water level. Okay, this was a soil mass, and this was the water level. Okay, this was all the water level, and this one is the impermeable strata. So that means beyond this water cannot pass. Okay, remaining the whole mass was soil. Okay, so this mass of soil is generally called as aquifer. Okay, this soil mass is generally called as aquifer, and this test name is basically called as unconfined flow pumping test. Okay, so this soil mass is generally called as aquifer, and the test is called as unconfined flow pumping test. Unconfined flow pumping test. Now, why it is called unconfined? If I go back to the image, if I go back to the diagram, this whole soil mass, this water layer, okay, initially it was like this, isn't it? It was here, the water layer is here. Finally, the water layer is here, isn't it? The final shape of the water layer is here. But this water layer is not confined by any impermeable strata above. There was a impermeable strata below. Okay, below there is a impermeable strata, but above there is no impermeable strata. Okay, so that's why it is called as unconfined. Okay, because if there would have been any impermeable strata like the one below, okay, if another impermeable strata would have been above, okay, then it would have been like a confined space of soil. Okay, that means if I now just try to elaborate by drawing it. So this was the sample. This was the main well, and these were the wells under study, and this one was the impermeable strata. So there was no impermeable strata above. Okay, but if there would have been any impermeable strata above, then how would it look like? Suppose, let me consider this one, another impermeable strata like this. Okay, and that means what? Now this aquifer, if I consider this aquifer is confined. In this case, this aquifer is confined, but in the previous case, this this impermeable strata was not there. Okay, so in the previous case it was a unconfined aquifer. Okay, so that's why we generally name the first field test as unconfined flow pumping test. Okay, now since there is no impermeable layer at the top, okay, that's why we call it unconfined. Now the second field test will be confined aquifer. It will be done with a confined aquifer in this manner. So in the second one there is this layer present. Okay, in the first one this layer was not present, so it was unconfined. I am repeating it again and again. In the first one this layer was not present, so it was unconfined. In the second one this layer is present, so it is confined. Okay, now if this is the water level, suppose initial water level is this one, and suppose after after you are pumping the water out at a constant rate, suppose q, then suppose the water level becomes like this. Suppose it becomes like this. Okay, and this we take it as the we can say thickness of the aquifer. D is the thickness of the aquifer. Okay, so now if I consider this one as H1, this one as H2, and this one as R1, and this one as R2. These are what? These are the observation wells. Okay, and this one was the main well. Okay, so from where you were doing the pumping. Now in this case the permeability, if it is this case of confined aquifer, the formula of permeability will be, I'll write it in the next slide. It will be K is equal to 2.3 Q by twice pi D log of 10 base R2 by R1 by H2 minus H1. So in this case this will be the formula for permeability. Okay, and this test is generally called as, sorry, this test is generally called as confined flow pumping test. Okay, so this is the difference. First test was unconfined, and second test is confined. Okay, where there is two impermeable layers. Okay, one is this one. Okay, and second one is this one. Okay, so these were the field tests that you need to know, okay, for uh, deriving permeability. Okay, so let us now go to the next topic. Let us discuss about effect of grain size on permeability. Okay, so effect of grain size on permeability. Now, grain size we basically deal about mainly D10. What is D10? I know you have got these terms D10, D30, D60, all those things, isn't it? You have got these terms. So if I take into example D10, suppose just for example D10 is equal to 2 mm. Okay, what does it mean? That means out of a sample, if you are taking a certain sample, so 10% of the, if you are taking a sample, okay, then 10% of the sample is 10% of the particles actually is finer than is finer than 2 mm. Okay, 10% of the sample is finer than 2 mm. So maybe 10%, suppose 1 kilo of sample you are taking. So 10% of 1 kilo means what? 100 gram, isn't it? If you are taking 1 kilo of a sample, 10% means 100 gram. So 100 gram of that sample is of size less than 2 mm. That means 100 gram of the sample, the particles are of size less than 2 mm. So that is D10. So there is a relationship between permeability and D10. Okay, so what is the relationship? Let us discuss. So this relationship is basically K is equal to C D10 square. Okay, that means K is proportional to square of the D10. Okay, and the thing is that this is done for clean sense. Okay, for clean sense with sense actually with D10 size between zero point 0.1 mm to 3 mm. Okay, this is for clean sense with D10 of size zero point 0.1 to 3 mm. Okay, and C varies. Okay, C, the value of C, it varies from 0.4 to 1.2. So C varies from 0.4 to 1.2. Okay, and generally the average value is 1. Okay, so this you need to please keep in mind. These are the these are some points which generally come in the exam, like this K is equal to C D10 square is a common question that is asked in the exams. They give you the value of D10, then C they give, so you can find out K, isn't it? So you please remember this formula. Okay. So whatever things I mention as important, this is all from my experience that I am speaking. Okay. So whatever things that I see say that are important, there is proof that these points have come in the exam. Okay, in various competitive examinations, I've got the proof. Okay, that these questions have come from various competitive examinations. So whenever I mention that any point is important and any point is a probable point which may come in the exam, please take it seriously. Okay, so let's move on. Now let us discuss about this k is equal to c d10 square. One more aspect of it. So in the equation that we have discussed just now, which was like k is equal to c d10 square, the unit of d10 was kept in mm. Okay, c was unitless and k was in centimeter per second. Okay, now another approximate equation that can be used for this is k is equal to 100 d10 square. Another, this is an approximate equation. Approximate equation that can be used. So where this k is in centimeter per second and d10 is in cm. Okay, and this equation is holding good. That means it holds good for k values which is less than equal to 10 to the power minus 3 centimeter per second. So for ranges of k is equal to 10 to the power minus 3 centimeter per second. Okay, and the unit of k you take it as centimeter per second and d10 is equal to centimeter. Then this equation holds good. Okay, so that is all you need to know. Please remember this formula as this ranges. Okay, then another important factor which can influence permeability. Uh, it can be discussed using one equation which is this one. K is equal to K is proportional to. Please write this down. So uh, this you know, this is what unit weight of water, and this one is the viscosity, isn't it? So if two soils are there, okay, having permeability K1 and K2, okay, then we can write K1 is to K2 is equal to like this. You can write it down. Okay, so generally this is not so common. This these terms, these terms, these two terms. Okay, obviously the below these terms are what? These are the viscosity, isn't it? These are the viscosity, and these are the unit weight. So it might not necessarily be the unit weight of water. Any fluid. Okay, suppose instead of water, another fluid is moving. Okay, through the soil. Okay, except water. it is not necessary that it is water. So any fluid, irrespective of water, if it passes through the soil, okay, then that unit weight of fluid can be considered in this case. Okay, so this K is proportional to actually unit weight, and K is inversely proportional to the viscosity. Okay, and this unit weight and viscosity are affected by temperature also. Unit weight and viscosity are affected by temperature. So indirectly we can say K is also affected by temperature. K is also affected by temperature. Because K is proportional to unit weight, K is indirectly proportional to viscosity. So, and both the unit weight and viscosity are affected by temperature. So indirectly K is also affected by temperature. So please remember this. For understanding it in a much proper way, let us do a very small numerical. And with this numerical, we will be ending the video lecture today. Okay, so let us get on with the very small numerical in order to understand it. Okay, so let us consider that the test was carried out at a temperature of suppose 25 °C. A test was carried out, and we have to estimate the permeability of the soil. Okay, so for porosity of 39%, okay, we have to estimate the permeability of the soil for a porosity of 39%, okay, and temperature of uh, 20 °C. Okay, so let us write it down. So the data is that at 25 °, the viscosity, if I consider mu1, the viscosity is 8.95, sorry, 8.95 millipoise, and at 20 ° the viscosity is 10.09 millipoise. Okay, and let us now move on with the next steps. So let us write down the main equation which we have discussed just a few minutes back. So K1 by K2 is equal to gamma 1 by mu1 is to gamma omega 2 by mu2. So I'll write it in a much better way. K1 is to K2, same thing, K1 is to K2 or K1 divided by K2. So now this one, there is nothing mentioned about the fluid. So nothing mentioned about fluid, so let us consider water. Okay, if there is nothing mentioned about fluid, that was consider it as water. And for water, generally the temperature difference of from 25 initially to 20 degree, initially it was 25 degree, isn't it? Initially it was 25 degree, finally it was 20 degree. So this temperature won't make any change in the unit weight of water. So this will get cancelled. This will not make much change. Okay, temperature effect can be neglected in unit weight of water for this small variation in temperature. So we can write K1 is to K2 is equal to 1 by mu1 is to 1 by mu2, or we can write K1 by K2 is equal to mu2 by mu1, or we can write K2 is equal to K1 into mu1 by mu2. Now let us complete the remaining steps. So K2 is equal to K1. Initially the K1 is not given actually, so let us take the value of K1. The initial value of K1 given, the data of K1 given is 1.72 into 10 to the power minus 1. Okay, so I missed it out maybe, so you put it here. Okay, so it will be 1.72 into 10 to the power minus 1 into mu1 is 8.95 by mu2 is 10.09. So ultimately you get 1.526 into 10 to the power minus 1. Okay, centimeter per second. Now this one is at E is equal to 0.79. Okay, so the thing is that this K2, this is the final, isn't it? K2 is the final. Okay, and final, at this final in condition, the temperature was 20 degree, isn't it? And the porosity given was 39%. Okay, porosity given was 39%. That means this is equal to 39%, or we can say 0.39. Okay, then what is void ratio? Void ratio is equal to n by 1 minus n. So it will be 0.39 by 1 minus 0.39. Okay, so quickly calculate how much in this will become. So this will become 0.64. Okay, so ultimately I can say that K2 is at E is equal to 0.64. Okay, and 20 degree centigrade. Okay, and K2 value we have already got 1.526 into 10 to the power minus 1. Okay, so this is all you need to know. So K, you have got K2 is equal to 1.526 into 10 to the power minus 1. K1 also you have got. Okay, K1 is 1.72 into 10 to the power minus 1. Okay, now this one is E2, isn't it? Because this was for K2. So K2 is E2. Okay, E2 is 0.64 because we have got it for porosity, isn't it, at 20 degrees centigrade. E2 we have got for porosity at 20 degrees centigrade, and 20 degree was the final condition. So that porosity will be also for the final condition. Okay, so uh, the void ratio we have got is for the final condition. Now how can we get E1? Okay, if you have not understood, I will just repeat. See, K2 we have got for K2 we have got for what, 20 degrees centigrade, isn't it? K2 we have got for 20 degrees centigrade, and we have got it for the porosity was given 0.39. Okay, it was for the second condition, and then this was N, and for that we got 0.64 void ratio. Okay, so this was E2. Okay, so this was E2, but we have not got it for E1. So in this case, I will leave it to you all. So how will you find E1? If you are being told in the question to again find E1 also, what was the void ratio in the initial stage? Void ratio in the final stage we have got from the porosity value of the final stage. Okay, because porosity was given in the final stage. So we can get it by this equation. K1 by K2 is equal to E1 cube by 1 plus E1 by E2 cube by 1 plus E2. So just put the values of K1, K2, then E2, and ultimately you will get the answer of E1. Okay, so we can find out the value of E1, and I hope you remember this equation. Okay, you remember this equation. I strongly believe you remember it. So in the assignment today that you will be submitting it before 10 a.m. tomorrow, you write the notes of this video and also you complete this numerical by finding out E1. Along with the numerical which you will be writing down, you also find out E1. Okay, and then you submit. Write down the notes of the video and complete the numerical by finding the value of E1. So thank you very much.